Hello everyone, my name is Dr. Arshad Khan. I'm a postdoctoral researcher here in the College of Science and Engineering, HBKU. On behalf of the organizers of this webinar, I welcome and thank you all for your presence. I'm so excited to have the opportunity to introduce our two speakers for this webinar on wearable electronics for COVID-19 applications. Our first speaker is Dr. Amin Barmak, who is currently a professor and associate dean in the College of Science and Engineering of HBKU. Dr. Barmak is a globally renowned researcher and academician having numerous achievements. He has previously held various positions in academia and industry in France, the UK, Australia, and Hong Kong. Dr. Barmak has published more than 250 research articles in top publishing venues and has designed more than 40 electronic chips. He has served on many editorial boards and is currently the editor of several prestigious IEEE transaction journals and the Nature scientific reports. Dr. Barmak is also an IEEE fellow and IEEE distinguished lecturer. Our second speaker is Dr. Salim Khan, who is currently a postdoctoral research fellow in College of Science and Engineering of HBKU. He was previously a scientific collaborator with EPFL in Switzerland. Dr. Khan has more than 10 years of experience in exploring printable materials and printing technologies. He has published more than 40 research articles, 2 patents, and a book chapter. He is also the recipient of various prestigious scholarships such as Brain Korea 21 Award, the Marie Curie Early Stage Researcher Award, and the ERC Fellow Award. Before starting the formal presentation, I want to make a brief announcement. We will be taking questions throughout the talks. So please type in your question in the Q&A window. The speaker will answer them at the end of the webinar. Without further delay, please join me in welcoming our first speaker, Professor Amin Barmak.
Good morning, everyone. Thank you, Dr. Arshad. It's a pleasure to be with you today. So today we're going to talk about wearable electronics for the COVID. So the title of the presentation will be Wearable Electronics for the COVID-19 applications. I would like to start by mentioning that we are witnessing a huge revolution in electronics. In the past, we started with the vacuum tube, the transistor, and then we are moving to the silicon technology based on silicon wafer, and also leading to the CMOS technology and integrated circuit design and VLSI, very large scale integration. But the future is actually supposed to be basically electronics that will be implemented on different substrate, not just the silicon. And we're talking about substrate that can be flexible, organic, and biocompatible substrate. This will lead to various and a huge number of applications in the area of biomedical, display, and also basically electronics. So the future is actually going to be beyond silicon. It's going to be printed electronics. And in this regard, we are witnessing a huge industrial interest in this area with an expected 1 billion market forecast by basically 2020 and beyond. And also a huge research interest by research labs around the world. So this is actually looking at the roadmap for IoT. IoT is really an emerging area today, and it is believed that IoT is driving the electronic industry for years to come. If you look at the IoT, which stands for Internet of Things, you will see that the wearable electronics is actually on the roadmap. And this is because wearable electronics can enable us to print electronics on very cheap and low-cost substrate, and therefore it can lead to the deployment at very large scale of electronic devices and also sensors. So if you look at basically the roadmap of IoT, there are 3 very important parameters, which is the communication, because you need to enable basically wireless communication of these devices to the internet. Because IoT stands for Internet of Things, which means that these devices will need to sense and also process the data and communicate it wirelessly. So communication is a very important parameter, but also cost will be as important, because you would like to deploy these devices at very large scale. In addition to that, there are other specific features such as low power. You need to operate at very low power. You need to have data security and data privacy. So within this context, we're going to talk about basically what can wearable electronics and IoT in general, which includes sensing and wireless communication, what can it offer for the COVID-19? So we'll start by talking about the motivation of this work. We're going to talk about, in general, wearable electronics. What are the application scenarios for COVID-19? What are the enabling technologies for wearable electronics that can be deployed eventually for COVID-19? What are the contribution of HBKU and our research interests nowadays? And then I will conclude and give you a future outlook. So the motivation will be really to build real-time monitoring of vital signs. And this real-time monitoring will be sensors and devices that can be wearable and produce reliable data. They need to be also biocompatible because they're going to be integrated very close to our body, and therefore they need to be biocompatible. They need to be integrated in different gadgets. I'm going to show you some of these gadgets that are emerging today. And also they need to be equipped with wireless communication. So when you talk about wearable electronics, it means it's wearables that can be deployed and can be basically integrated into gadgets that will be very close to our human body. You all know the smartwatch, for example, from Apple. You all know, for example, the smart glasses from Google. And also there are many other devices that are emerging, such as the smart belt, even electronics that is integrated in our textile and clothing, for example, the smart pants, smart shirt, and people are talking about smart shoes as well for applications like in sport. So if you look at this area, the interest from industry and also from the research community has been exponentially growing. So if you look at, for example, the number of papers that have been published just last year in this area of wearable electronics, we're talking about over 2,000 papers as compared to less than 100 in 2013. And the market share of this area is also growing very rapidly, especially in areas related to healthcare, defense, fitness and well-being, and also sports. So it is expected that this market will reach basically something in the order of $100 billion by 2022. So it's an area that is growing very, very fast. So what are we talking about here? What are the basically sensors that we can deploy at very large scale, but also very close to our body? So we're talking about sensors like temperature. You can monitor respiration, the respiratory sensor, pulse rate, position sensor, motion sensor, for example, hydration sensor, air quality sensors, and also gases. So for example, you can analyze the exhale or the breathing, which can give you some indication of about some biomarkers in your body. Also pressure sensor to detect, for example, respiration and other things. Also glucose sensor have been emerging recently. Just to give you an idea about the potential of wearable electronics, if you are able to integrate all of the sensors in gadgets and in a wearable way. Just think about, for example, I would like to bring this example. I like this example. I would like to bring this example. Just think about Uber. Uber is a multi-billion company that is, the business model of Uber is just based on the physical location of customers. So you want to go from point A to point B, all they need to know in Uber to manage their business is basically to know your location and where you want to be. So you are talking about only one parameter, which is the position. So I would like to ask you the question, what would be the potential for new industries if we are able to implement all of these sensing parameters, not just location, but you're talking about motion, hydration, gases, pressure, glucose, temperature, respiration, pulse rate, and so on. So I think the limit is the sky, and there is huge potential in wearable electronics because they can open up opportunities for many industries in the future. So let me show you a little bit of the state of the art. What are the wearable electronics devices that exist today in the market, either at the research stage or in terms of product. So at the research stage, and also some of the products have emerged, we're witnessing basically wearable chemical and electrochemical sensors. So for example, we are witnessing wearable glucose sensors that can be implemented as a patch. So they are very non-invasive. We also have wearable lactile sensors that emerged recently. These are papers that are published in very top venues, for example, Nature. Lactite will be a metabolite of interest in bodily fluids, so they detect the sweat, and they can actually generate some biomarkers related to your health and fitness. We also witnessing a lot of sensors related to pH sensor that can also be wearable. And all of these sensors are actually electrochemical sensor. They are embedded with the human epidemics targeting bioanalyte present in the human sweat, saliva, or tears. And also they are equipped with data transmission, wireless communication. In terms of sensors, the state of the art today, we're able to integrate wearable pulse sensors. This already has been published in many papers. A respiratory sensor is becoming a reality today. Temperature sensor also for the body is being used today, and also motion sensing. So most of these sensors are deployed for fitness, outdoor activity, health monitoring, and also most of them are actually resistive, capacitive, or piezoelectric. So they generate bioscience signals that are basically processed using an onboard detection system and electronics that is integrated together with the sensor, and also they integrate the wireless communication. So how can we apply this in the COVID era? So the world is changing with the pandemic today, and the question is, how can we integrate these sensors to help us with the COVID crisis? I think we can start with the common physiological signs that we can see in COVID patient. So you have very high fever after infection. You have extreme and irregular cough, dryness of cough as well. Heart rate that increases. In fact, it is believed that it will increase by around 8 beats per minute for every 1 degree increase in terms of the temperature. And also fatigue and restless, these are also signs of and symptoms of COVID. So if we are able to implement a wireless monitoring platform, wearable platform, then we can reduce the burden of medical systems. We can have early detection of symptoms. And we can also, with the help of data analytics and AI, we can generate early warning system to tell us basically the evolution of the COVID-19. These are actually examples of very recent development that happened recently, and mainly targeting COVID. For example, this UCSD, University of California, San Diego, they actually implemented a wearable system that can detect the level of vitamin C in human sweat. There is this company, which is an Illinois-based company called BTW Tag, and they are actually doing contact tracing solution for COVID using a portable device, but include basically wireless communication also. There is also a Chinese tech giant, Huami. They actually designed a mask which is self-disinfects itself, and also can be used in order to unlock the iPhone using the face mask. And also, most recently, researchers at Northwestern University in Chicago, basically they developed a patch, a wearable patch, and that can monitor respiration and cough. And this was done in just last month. And the idea would be to monitor symptoms related to COVID-19. So there is a lot of research using this opportunity and looking at basically wearable devices that can be integrated for the COVID-19. So what are the key enabler technologies for wearable electronics? What do we need for wearable electronics? So you can think about it as printing devices on flexible substrate. So your substrate can be anything. It can be rollable plastic, it can be paper, it can be fabric, for example. These are the substrate. And then you need to print material on the substrate in order to build devices. So for example, people use ink, which is widely available today, ink of material, and then you can use manufacturing through printing using different techniques such as inkjet printing, which we have at HBKU. You can have also screen printing, coating techniques, and also different type of chemical processing in order to deposit this ink onto substrate. So that's the idea. You have flexible substrate, can be anything, and you try to through techniques, inkjet printing or coating, you can actually deposit this pattern at very low resolution. We're talking about very high resolution. We're talking about micrometer scale. So inkjet printing can do, for example, micrometer scale. So these are actually the equipment that we have at HBKU. We have inkjet printing, so we can do basically inkjet printing on any substrate, including paper, including plastic, and including also fabric. We also have some kind of substrate treatment facilities because we need to treat the substrate after you do your deposition. And also, once you have the device, you need to characterize it. So we have a characterization facility at HBKU, which includes probing stations, different imaging techniques in order to image the structure and to study its characteristic and its parameters. before testing the device. So in a nutshell, how can we wield these sensors? I want to give you a very simple example in order to understand the physical phenomena behind it. So basically, you start with any substrate, let's say paper, plastic, or whatever, and then you are able to deposit this ink, dropping this ink at a regulated frequency that you can regulate and a diameter that you can regulate. We're talking about micro scale. So you can deposit straps and electrode, you can build pattern because you are printing these devices using this inkjet printer, and you can end up, let's say, with an electrode that you implement on any substrate. So if you think about it, if you have, let's say, just a conductor, a wire, we know that, for example, if we apply a current on this wire, then the current that flows, we apply voltage, and the current that flows through the wire will have a certain resistance that depends on temperature. Because if temperature increases or decreases, basically the speed of electron within the wire will be different, and therefore the current is different. The resistance is going to vary. So by having a variation of resistance that depends on the temperature, I can build a temperature sensor. So I'm trying to explain it in a very simple way. And another simple way that I can show you another device is, for example, we implement this interdigited electrodes, or you can have two electrodes, and in between you deposit a dielectric, you deposit another material. This material, for example, can be sensitive to humidity, so it can basically absorb water molecules. So what you have is actually a capacitor. You end up with a capacitor because you have two plates and a dielectric. And then your dielectric is sensitive to water molecules, which means it's going to have different characteristics depending on the level of humidity in the room. Therefore, you can end up with a capacitor where the value would depend on the humidity, and you can build the humidity sensor. So humidity sensor can be built using, for example, capacitive devices where we have the electric that absorbs the molecule of water, and the permittivity of the capacitance will change, and therefore the capacitance will change, and I can build the sensor based on that. To build, for example, a cough sensor, you can actually use a strength sensing detected through stretchable textile fiber. So you have a textile fiber, you deposit some nanomaterial on top of it, and as you stretch basically your wire or your material, what's going to happen is, because it's a nano material device, so you have less connection or more connection between these nanostructures, and therefore your resistance can vary. So you can actually build, let's say, a very small micro pressure sensor just based on this principle, because you have nanostructures that will connect or disconnect depending on the stretching of the materials. So we can build various sensors based on very simple ideas. VOC sensors or gas sensors can be also built because you can actually deposit a sensing film on the substrate. The sensing film can be, let's say, tin oxide, for example. We know that tin oxide, when exposed to gases, it's going to have an oxidation reaction. If you have an oxidation reaction, it means that you give up an electron, or you have an extra electron in the structure, and therefore your resistance is going to change. If resistance is going to change, you can actually react to the gases that you have in the environment. So various sensors can be built, and the example that I gave you here is capacitive or resistive. But in fact, today we can even build active devices with wearable electronics. We can even build a transistor on a wearable or stretchable substrate today. So this area is evolving very rapidly, and as you can see, the principle behind is quite simple. Let me show you some of the HBKU wearable systems that we have implemented so far. Actually, we built many systems based on this wearable and printable electronics. We built actually QFit, which is like a smart watch. I'm going to talk about it a bit later. It's very different from what you have with iPhone, for example, watch, but it's actually very low cost and actually very low power, and also the range is much beyond just the 10 meter of a Bluetooth device. We also built a smart belt that can monitor breathing and respiration. We are working on a smart mask for COVID today, and this can detect temperature, coughing, as well as basically respiration of the patient. We are working also on a smart glove to detect dangerous gases. Let's say workers in QP, they go to various areas in the plant of Qatar Petroleum, and in some areas, maybe you can have some dangerous gases that you need to detect, and a smart glove actually can detect that. We also designed very successfully a smart diaper. So it's actually a wearable sensor that can be attached to the diaper of a baby, and you can monitor whether the baby is breathing and his temperature and whether the diaper is humid or not. And it can send this information to, let's say, the smartphone of the mom that is in the house, basically. So to build the systems, it's actually not only building the sensor. You have to come up with the sensor, but also you have to read the signal from the sensor, which is typically an analog signal. It's a noisy signal, and also it's a very weak signal. So you need a lot of amplification, filtering the noise, and also signal conditioning before you can use that signal, because typically the signal coming from the sensor is very weak. Once I have my analog signal, then you need to convert it in digital domain in order to process it in an easy way. And in order to add, let's say, AI algorithm and so on, you need to operate in the digital domain. So you need an analog to digital converter, a microcontroller to process the data, and also a wireless communication. This is in a nutshell at the bottom what you can use. You have the printed sensor patch. You need a readout. For example, it can be voltage divider if it is a resistive, because if I have a variation of resistance, I can put another resistance here, apply voltage, and I can read the variation of voltage at the output, but I can convert into a digital format. Once you have this signal, you need to convert it to digital format. This can be included in the microcontroller, and also you have the Bluetooth communication. So basically what we are doing in my lab is not just to work on the sensor, but also to work on the full processing chain. So we go from the analog sensor signal, we go to filtering, signal conditioning, readout, we go to the ADC, convert the data into digital, and we process the data in a microcontroller. And in some instances, we even use AI algorithm. For example, in the case of detection of gases, when you detect the gases, you need to classify them. So we need a classifier, and we use machine learning to do that. These are some examples of the systems that we have built. So for example, for the watch, actually, not only we build the sensor and embed them within the watch, we also included the Bluetooth communication protocol, and the data is connected to control station. And then after that, all the data is stored in the cloud. So we host a website where you can actually go to a website, and then you can access basically the data of all patients that are wearing the watch. And then we have also graphical user interface, GUI, on a web browser, so you can actually access the data anywhere at any time. So there is also the software part that goes with it, which is storing the data in the cloud and also accessing it through a graphical user interface. This is actually showing some of the results that we have. So you can see actually for this watch, what we wanted to achieve is really very low cost, because it's supposed to be deployed for workers in the field. This is actually a project in collaboration with Spring Committee. So if you want to have these watches deployed, let's say for a worker in the stadium, for let's say hundreds of workers in the stadium, there are many challenges. The first one, it has to be very low cost, because you want to deploy it to all workers within the Qatar. So the watch that we designed is actually less than $20 US. It has to be a very low power, because you don't want to charge the battery, let's say every day. You have to charge it, let's say even every month will be better. So the autonomy of the device that we have is about 2 weeks. And in addition to that, because you want it to be very low power, you don't want to use basically GSM, because you need a SIM card. And if you need a SIM card in order to communicate, it means you need to pay subscription fee. And therefore, you have a very high capital cost and operational cost for your system. So what we did is actually, we based this on Bluetooth. And as you know, Bluetooth BLE, Bluetooth low energy, it has a very limited range, which is about 10 meters. And we want to cover a larger area. We want to cover hundreds of meters. And therefore, we come up with actually a wireless communication protocol that we implemented in the lab. And the idea is actually to use all of these basically nodes as routers, and therefore you can collaborate together to increase the range of basically the device. So we can cover over 250 meter range using only Bluetooth and using very low power communication protocol. Some of the features of this work is that you can have hundreds of concurrent users, hundreds of people that are connected to the platform. As you can see, this is the name of the people, and we can see their health status. If it is green, it means they are okay. If it is red, it means they are suffering from maybe high heart rate, high temperature, maybe temperature stress, and so on. And we can look at each one of them individually and we can see the pattern in terms of temperature, heartbeat, and so on. We can access the data individually, anywhere, anytime. So the features are actually 2 weeks of battery life. You have hundreds of concurrent users at the same time. We have an extended range of 250 square meter using only actually Bluetooth, which is a very, very significant achievement. Very low capital and operational cost, and also mass production capabilities. Everything was made actually in Qatar, even including the 3D design, the 3D printing of the housing of the electronics. So this is actually another project that is progressing very, very nicely. In fact, we have a patent on this that is in progress. So basically, this is a face mask that we are developing in the lab, and it's actually embedded with sensors. The sensors are fabricated on a thin substrate, and then they're transferred on the mask. They're transferred on the fabric of the mask. You can monitor vital signs, including temperature. In fact, the temperature is quite accurate because you're looking at the exhale temperature, so it's deep body temperature. You can actually detect the respiration, whether it's normal or abnormal. We can detect the cough, and we can also detect the humidity level of the cough, so we know if the cough is dry or not. And in addition to that, we are recently working on location. So basically, not only you're gonna detect basically all these parameters, but we can use actually, without GPS, we can actually use triangulation techniques in order to detect the position of the user. So you can think about it as all of these temperature and respiration, cough sensors, and so on. They are integrated on a very low cost patch, and this patch is actually integrated into the fabric of the mask. And then there are wires that will connect to a detachable module, and this detachable module will basically include the microcontroller and the wireless communication. Why detachable? Because you don't want to integrate all the electronics into the mask. Otherwise, your mask not only will be very expensive, because the sensors are very low cost, but then the detachable module, which includes the controller and the wireless communication, will be in the order of, let's say, 15 to 20 US dollar. So you don't want to put that 20 or 15 US dollar in every mask. So the idea is to have a module that you can reuse, and you just detach it, you use the mask, you throw it. When you have a new mask, you just plug basically the detachable module, which will include the microcontroller, the BLE, and the communication, basically. So as I said, we are in the process of filing a patent on this idea. And we have also other recent projects, which include a smart glove, as you can see here, so the smart diaper. And also, if you come to our lab, you visit our lab, you will see that we have a multi-sensing prototype that we put on basically a mannequin. And we're trying to implement all of these sensors, including the chest and also the fabric of the t-shirt and so on. This is also one of the projects that we are working on, trying to integrate these sensors into a shirt and a smart belt in order to detect various parameters, including heartbeat and respiration and so on. And again, we use this concept where you have a detachable module, and the expensive electronics will be on the detachable module. However, all the very low cost electronics and sensing will be integrated and embedded into the clothing, and it will be wearable. So if basically when I explain the concept of how these sensors work, it may sound that it's very, very easy, because you have just, let's say, a metal wire, you inject a voltage, and you measure the current. Basically, this will give you variation of resistance, and this resistance will depend on temperature. It may sound very easy, but in fact, it's much more challenging than that. I will give you just an example of the challenge so you can understand why this is not very mature technology and it's still in the research phase. So if you use just a simple wire, which we call resistant temperature detector, RTD, so a simple wire where you try to measure the resistance as a function of temperature. So if you try to make this sensor wearable, you're gonna integrate it into a patch in your clothing. And as you breathe, as you move and so on, basically this patch is gonna be stretched and compressed, depending on your movement. So when you compress it, actually, because it's nanomaterial, the resistance is gonna change, because the connection between this structure of the nanomaterial is gonna have different pattern, and therefore the resistance is gonna change. This is actually shown in this experimental measurement. So you can see here if I have a bending and a different radius, strong bending or small bending, then you have a variation of resistance. So this is a problem because the resistance is not going to change only with temperature, but it's going to be changing with the bending of your wearable sensor. To overcome that, so we come up with this very interesting idea. Actually, one of my postdocs came up with this design, Showkat. So basically, instead of having only one substrate on your sensor, what you can do is you can actually have the substrate and you're going to paint the sensor on both sides. So if you experience some bending and stretching, it's going to be in a differential way. What does it mean? It means if this side is bending, is compressed, the other side is being stretched. And therefore, one resistance will increase, the other will decrease. So if you can think about it as these two sensors on both sides of the substrate, you will have resistor A and resistor B. One of the resistance is going to be increasing as function of bending, and the other will be decreasing. So the idea, instead of reading only one resistance, is to read the two resistances in a differential way. If you do that and you look at the difference, then as function of bending, you end up with a constant because one is increasing, the other is decreasing. I just do it in a differential way, and therefore I have my resistance that is constant as function of bending, and then your resistance is going to depend on temperature only, which is what we want. So this is not only improving on getting rid of the stretching and bending in the readout of the sensor value, but also it will increase the signal-to-noise ratio. Why? Because if you read in a differential way, you increase, basically, you double the sensitivity. This is one. Second, you also get rid of the common mode noise, because if you have any noise that will be superimposed on one resistor, it will be the same common mode noise that will superimpose on the second resistance. If you read in a differential way, you get rid of the common mode noise. So in a nutshell, what I'm trying to explain here, I just pick an example here. What I'm trying to say is not as easy as you may think. It's not just printing these devices and so on. You have to come up with basically smart readout strategies and smart structures in order to cancel the noise, to improve the signal-to-noise ratio, and to make your signal readable. For example, if you want to build a temperature sensor, it has to be dependent only on temperature. It cannot be dependent on the stretching of the basically bending and so on of the device in the wearable setting. So I would like to turn the floor now to my colleague Salim, who will be presenting the second part. I wanted him to present the second part because actually he's the one who basically, together with other colleagues, they built this platform in the lab, and we are able now to design all type of sensors. So he's going to explain how these sensors are integrated at HBKU Sensors Lab. Let me pass the floor to Salim now, who will continue with the slides.
Yeah, before moving to the next speaker, a quick reminder for those who joined us late. If you have any question, please type them in the Q&A window. The speaker will answer them at the end of the presentation. Thank you. So now, without further ado, let's give the platform to Dr. Salim.
Hello, everyone. I will continue with the experimental part of our activities. So here are a few of the representative examples that we have developed in the previously wearable gadgets that we have seen in our previous slides. So we will start with the printed sensors, the fabrication protocol, what we do while developing these sensors. So in this slide, we can see actually this is the printed sensors are any structure transducer. It contains two main different constituents, like one patterning and a deposition or sensing layer. So for patterning, we are using our inkjet technology, where we have an ink reservoir. These are commercial devices now available here. They are coming with equipped tools. So the ink reservoir is connected with multiple nozzles. So in our case, there are 16 nozzles, and they are the voltage is modulated in such a way that with each pulse here they are driven by a piezoelectric actuator. So with each pulse actuation, it ejects a droplet. And these droplets are tuned in such a way that their frequency and their droplet size, so that the final devices or the final structures that we achieve on a substrate are continuous lines are a uniform layer. Here in this case, you can see that droplets are ejected at specific frequency. And the blue color here, we have any arbitrary substrate like flexible substrates. In our case, we are usually using PET plastic substrates or textile carton-based or paper substrates. And here the patterns are any metallic conductor. Here they are actually representing interdigital electrodes. So for interdigital electrodes, we need metal inks. So these are designed in, first they are designed in a software and then they are exported in the inkjet system. And the parameters are tuned and we achieve results such as these. These are the printed patterns. This is silver lines which are printed on PET substrates. And there are different steps that we achieve before, like pre-treatment and post-treatments. And these are the annealed structures that we achieve finally after doing our printing. So these substrates, they have a specific requirement, like the surface function, the surface properties are also dependent on the rheological properties of the solution. So all these interactions, they result into a very uniform structures, and these are really important so that we can achieve a very specific and precise distance, because in some cases we are using wide area metal oxide, the materials which have a wide band gap. So in order to have a quick response, we need to reduce this sizes. So the substrate treatments and the function of the properties of the solution, they are really interdependent, and we can tune all these properties to achieve a very uniform layers like these. Here in this case, we can see there is a bit variation, but still they are in acceptable ranges, like they are negligible in few nanometer, a few micrometer, fraction of microseconds, micrometers. And here in the second slide, you can see we can have a multiple structure, like not only a single layer. Here, this is the first layer that we have printed silver, and the second layer, we can use even the same technology or a complementary technology for thin film deposition, because for thin film deposition, there are complementary steps to deposit the sensing layer. Here, in this case, you can see this one, this is deposited by a thin film applicator, and the size of the thickness of the layer can be controlled by controlling the thickness or the standoffs in the system that are adjustable. So once we print using inkjet technology, these patterns, they are achieved, they are centered in oven, and then they are placed in such a way that to avoid interconnections or deposition on the contact pads, we just deposit the sensing layer on the respective area or in the interdigital electrodes. So this is how the printing works. So the printing protocol, as I explained earlier, that the substrate preparation, it contains different cleaning steps, because we have to remove any dust particles or any accidents that are already deposited on the substrate, because the chemical, most of the solutions, they are chemical based or colloidal solutions. So we need to avoid the spreading out of the solution on the substrates. And this is the protocol. First, we tune the material so that we achieve a uniform synchronous droplets. As you can see here, this is a picture taken from the system. Here we have a very synchronous deposition of these droplets. So the speed of the droplet, we can control the frequency of the droplets, the resolution, final resolution on the substrates are actually dependent on the frequency and the speed of the droplets. And then the droplets are, these parameters are, we tune this, the droplet spacing, we keep such that we achieve very uniform layers. And here we first do deposition on the substrate, we record the droplet size, and then we adjust the droplet spacing so that we achieve this type of lines or patterns on the target substrates. There are certain post-treatment, post-printing treatments where we keep the substrate in the oven, like pre-treatment first stage, so that to remove any solvents, surfactants in the solution, and then we keep it in the specific temperature. Usually these substrates are plastics, and they sustain temperatures till 150 degrees centigrade. And these solutions are prepared such that all the surfactants, they are removed from the material after deposition, at these specific temperatures, either before 150 or right at 150 degrees centigrade. And then some physical and optical characterizations are done to achieve, to see that what you were looking for, the desired thicknesses or the mismatches in the boundaries, or any adhesion loss tests, because we are using multiple substrates, and the adhesion loss is really important because, as Dr. Amin mentioned, that we are doing this bending tests. So for bending, we need to find the right curvature, bending curvature, and in order to achieve that specific adhesion, we test our material and do the pre-treatment conditions, tune the pre-treatment conditions, so that to achieve proper strong adhesion. When we bend the substrates, the material or the patterns, they do not delaminate from the substrate. So these are the different printing protocols that I will now come quickly to the temperature sensors, the individual discrete sensors that we have developed. And this for the temperature sensor, which is worn on a human body. Here, beside the RTDs, we have explored using RTD structures and putting a temperature sensing layer where we use carbon paste. And this carbon paste is actually a mixture of carbon black powder and a thermoplastic solution, thermoplastic material, where when we bend it, they do not lose their conductive properties. And also they are very sensitive. We do not compromise on the thermal properties of the solution of the sensor. So here we have interdigital electrodes printed from a silver solution, which is commercially available. And also here is a device that we have printed already. And here, after printing the device, we have done the thermal characterization against the temperature. So these are actually resistive structures. And here we can see the sensor mounted on the human body. And here you can see the rise and fall when we touch the substrate. And here the human body temperature is recorded using these sensors. Similarly, the humidity sensors, as we have seen in the previous slides, is interdigital electrodes, and you can see the sensing layer. It works on the conductivity change. The methyl red solution is used, and we tune the conductivity when the material of the water molecules are deposited in the sensing layer. And here we can see we have this fabrication steps, and all these are developed using printing technology. The interdigital electrodes are developed by using inkjet technology, and this casting technique is adopted for deposition of this methyl red solution. And here we can see the sensitivity of the characterization results for the sensitivity and the impedance response of the sensor. Similarly, the respiratory sensor, actually we are exploiting the temperature of the exhale and inhale peaks that we can utilize in the mask, in the smart mask. So in the simultaneously, we are able to record the human body temperature, and from these inhale and exhale, because there is instantaneous change in the temperature, where we can these peaks can be correlated to the normal or fast breathing. And here we have these are the tested results in the lab using this patch, the sensor patch, which was developed using inkjet technology. Similarly, the cuff sensor was developed by impregnating the cotton fabric, which is stretchable. And this technique is really interesting, and it's giving a very promising results. And this technique is we use this silver solution to impregnate, or the percolation mechanism to be more precise. So it dissolves the material and the fabric, and then when we stretch the material, it works in the similar fashion like strain sensor. When we stretch it, the resistance, these threads, they interconnect more strongly, and the conductivity is increased. So this phenomenon we can use like for a very minute changes, just like cuff. So because with the cuff we have an impulsive force like that is correlated with the strain of this fabric, and we are able to utilize these mechanism for the cuff sensing. So this work we have demonstrated practically in the lab. Similarly, the volatile organic compound sensing, which are really important for monitoring the human breath, and also for, as we have seen, they are more also suitable for using in the glove in the smart glove. where we can use, we have demonstrated these sensors on 3 different substrates, and we have tested 3 different gases, ethanol, isopropanol, and acetone. And we have tested it against 2 different concentrations of these, in 4 ppm or 22 ppm parts per million. And they are really responsive here, we can see. So these were actually the substrate demonstration, substrate comparison, comparator study. And here we can see that the PET substrates, they have shown good promising results against these different gases. So all these sensors, they were printed and using inkjet technology and deposition technique using screen printing. So here are these patches. We have tested distributely these sensors. This similar patch, we are using multiple sensors like temperature sensor, cough sensor, VOC sensor. And here are the results that are the sensors which were tested individually. And here is the design. This one shows the design. And here is the mask which we have placed the patch, sensor patch on the mask. Now, currently, we are working on a new approach where we can use a transferable technology, which is more convenient, because here we, in that we deposit the printed structures on a donor substrate, and then we use thermal lamination and deposit directly on the substrate, where we will avoid the combination of the delamination. Here, in this case, we are using by adhesive tape that we can remove. So these were the different sensors that we fabricated and we tested in the lab. So now we'll hand over the next conclusion part to Professor Amin Barmak, that he will conclude the presentation.
So basically, in conclusion, just let me share my slide. In conclusion, we can say that wearable electronics constitute a very important pillar for IoT, because they can enable very low-cost wearable sensors. Low-cost wearable electronics for health monitoring, healthcare monitoring present huge potential. Real-time monitoring of vital signs in human body are demonstrated in this presentation. We can actually use them in order to monitor physiological science in COVID. And key enable technologies are material manufacturing. And above all, you have to come up with innovative architecture, such as the differential readout that we have explained. Printed and wearable sensors are developed in HBKU, and we have shared with you some of the prototype that we have done. We are not just interested in the sensor, but we build the whole system together with the wireless communication, and also the sensing, the readout, and the ADC. And in some instances, we even integrate AI together with the platform. So as an acknowledgement, I would like to thank the College of Science and Engineering for supporting the sensor research, in particular Dr. Munir Hamdi, our dean. I would like to thank my group. Many people have contributed to this, not only Salim. There are many people behind the scene, and also many PhD students and other postdocs. I would like to also thank QNRF for supporting our research, mainly in 2 grants that are ongoing today. And also as well the Spring Committee for Legacy and Delivery, who have supported us with other projects related to basically the workers. Without any further ado, I would like to thank you for attending the webinar, and we will be very happy to answer any questions you may have.
Thanks for your insight into this most important topic that I know affects all of us here. Now I would like to open the floor for the questions. Here is the list of the selected questions from the audience that I have compiled for both speakers, Professor Amin and Dr. Salim. Please have a look and respond them accordingly.
Thank you very much. Maybe I can start, and Dr. Salim, if you have anything, you can add to my answers. So let me start with question 1: why wearable electronics are an integral part of the IoT roadmap? The IoT roadmap means that you need to deploy sensors at very, very, very large scale, and at the same time they need to be very low cost. And this is exactly what wearable electronics can offer, because you are printing the sensors on different substrate, and you can actually print massively on basically at large scale. And therefore, that's why if you look at the roadmap for IoT, it really includes wearable electronics, because they offer massive and large deployment, but at the same time, low cost. I think this is the answer for question 1. Question 2, where is wearable electronics a mature technology? What are the main difficulties in making it a reality? I would say not all sensors are mature, and it didn't hit the commercial, basically commercial landscape yet. And this is mainly due to a lot of difficulties, because when you build the sensor, your sensor can respond to many things. You cannot be selective. That's the main maturity issue of wearable electronics. So for example, we have seen the example when I was talking about my presentation, we have seen the example of temperature sensors. So you have a temperature sensor that also is sensitive to, it can be sensitive to humidity, it can be also sensitive to basically the stress on the wearable device. So you need to come up with innovative architecture, such as differential readout that I have shown you, and other type of technologies in order to overcome these issues. So the short answer, wearable electronics is not yet very mature, but I think with innovative design, it can be a reality today for a lot of applications. Third question, what are the advantages of QFit compared to existing smartwatches such as Apple? I think the first advantage is cost, because we are able to integrate the QFit smartwatch in our lab at a cost of less than $20 US. This is the first advantage. Second advantage is that you don't need a smartphone next to it. Any iPhone, smartwatch, or Samsung or whatever, you need to have a smartphone next to it so that you can connect to the Bluetooth. In our case, we cannot afford to do that because we are planning to deploy this at very large scale, let's say in construction sites. You don't expect the workers in the construction site to have a smartphone. And therefore, the main difference with Apple Watch is that it uses a custom wireless communication protocol that we built ourselves. And we try to extend the range of Bluetooth, because we know Bluetooth is only a few meters, and construction sites can be hundreds of meters. So these are the main differences. So low power, it doesn't connect to a smartwatch. It relies on connectivity that is very low cost, yet extending the range of a simple Bluetooth device using our custom wireless communication platform. So this makes our watch lifetime is about 2 to 3 weeks. You don't need to charge it for 2 to 3 weeks. An Apple Watch, you need to charge it every day. The next question is the system that you implemented, such as QFit. Does it include the GPS chip? And do you integrate localization feature? As you know, localization is done very easily with a GPS chip. In our device, in our watch, we didn't have a GPS chip because we wanted to keep the cost very low. So in order to implement localization, in fact, it's not fully implemented, but we are working on it. So the idea is actually, instead of having a GPS, what you can do is, because you have your watch that is communicating, let's say, with multiple base stations. Base stations are actually just a Bluetooth device that you put in the field. So if your watch is communicating with, let's say, 3 base stations, the idea is to use the strength of the signal in order to know how far you are from each base station, and you can encode that signal. So if you know the strength of the signal, let's say with respect to 3 stations, then because you know roughly the strength of the signal, you can know roughly the distance, and you can use triangulation to localize basically the watch, because you can actually, if you have a distance to 2 points or 3 points, you can very accurately know what is the location, exact location of that particular watch. Next question, have you looked into the privacy security aspect of data collection? To be honest, we didn't work on this area yet. And we're trying to collaborate with other colleagues at the College of Science and Engineering in order to look at privacy and security. I'm not an expert in that, and we need to collaborate in the future with other colleagues to do that. The next question, question 6, for long-term field applications, does the printed sensor suffer from any aging effect? This is a very interesting question. The answer to that, yes. This is in the sensor area, this is called the drift. So after using the sensor over time, usually the response will drift. So to compensate for that, we have to use basically innovative readout architecture, where you try to read in a differential way. And also every time your baseline is changing, you have to take into consideration that new baseline. So in order to compensate for that, typically what we do is you sample the signal when there is no presence of any analyte or any parameter that you want to detect. And then after you get the response, you try to read in a differential way. So you don't read the absolute value of the sensor, but also you always do it in a differential way. So you sample the baseline, and then you sample the response of the sensor, and you try to look at the difference rather than looking at the absolute value. This will give you some compensation of what we call the drift. Other ideas would be also to include this in our detection algorithm, so we can have AI and training in order to train basically the drift of the sensor in the algorithm. And these are some solutions that we are exploring in the future. I think I have answered most of the questions. Salim, if you want to add anything, you are welcome to. Otherwise, I leave the floor to Dr. Arshad again.
Yeah, Professor, I agree with you, all the questions. They were really accurate answers to all the questions. Thank you.
This most important topic again, that I know that affects all of us here in this pandemic era. And thank you all the audience for attending this webinar. Thank you.
Thank you.